Hello, we're going to talk about inverse functions. This is our first lecture in the spring semester. Before defining inverse functions, we have to make sure we understand what is a function. And in mathematics, function is an object consisting of three components. The function has a domain, df. It has a range, rf. This is standing for range. And there is some formula, some equation, some rule that for every x in the domain, we put in correspondence y, which is fx, in the range. So such a diagram, x belongs to the domain. We call these originals. And we move to y, which is f of x, in the range of the function. Every x, there should be only one image y in the range. We cannot assign to x two different images. For functions, we can use the vertical test, vertical line test. Which tells you when a graph defines a function. So let's say you have a graph like that in the xy plane. You have a graph like that. This graph, as drawn here, does not define a function, because if you take one x somewhere here, and you take a vertical line, it cuts in two different places, and there will be two different y's corresponding to this x, two different levels. Now, we want to define one-to-one functions, or simply one-to-one functions. These are functions where every image has only one original. Every image y equals fx in the range of the function has only one original x in the domain. We can also say that a function is one-to-one if different originals, if x1 is different from x2 in the domain, then the images are different. Why? We can write it this way. fx1 will be different from fx2. Let's see some examples. If you take the function fx equals x squared, natural domain for this function is the entire number line, from minus to plus infinity. For every such x, we can define x squared. This function is not one-to-one. Let's look at the graph of the function. It will be like that, a parabola. And there will be images, let's say one to be one image with two different originals. Here on the right side and on the left side. Negative 1 goes to 1, and 1 also goes to 1. F negative 1 equals F1. So we have two different originals for this image 1. However, if we take the function fx equals x squared, a different domain, if you take the domain now to be only positive numbers, the graph of the function will be only this part of the parabola. And this function is 1 to 1. For every originals we choose on the y-axis, so let's take a point here y, we can find, for every image y, we can find only one original x. So we have a test, easy geometrical test, which we can call horizontal line test. We take horizontal lines and we want them to cut the graph only once. For instance, if you have a graph like this, it does not satisfy the horizontal line test. It will cut in 3 different places. So the function corresponding to this graph is not 1 to 1. There will be 3 different originals for this value here, if this is y, if altitude is y. And our original example with the parabola, this parabola here, does not satisfy the horizontal line test, because you see, you can take horizontal lines, they cut twice here. So every horizontal line should cut the graph at most once. Every horizontal line cuts the graph at most once. This is a test for f to be 1 to 1. Another simple test is looking at the derivative, if the derivative exists. We can call it derivative test. If the derivative of the function is different from 0 on some interval ab, then fx is 1 to 1 on the closed interval ab. If the derivative is not 0, it means it's either positive or negative. So the function is either growing or decreasing, and such functions are 1 to 1. So if the function is decreasing like that, it undergoes the horizontal line test. If it's increasing like that, also every horizontal line cuts the graph only once. So that's a good, important derivative test, easy to check for many functions. Now I'm ready to define inverse functions. Here is a definition. Definition of inverse function. And inverse functions, we write f negative first power, which is not power actually, it's just a notation for the inverse function. It looks like a reciprocal, it's not. This is not 1 over f. It's a notation for inverse function. And on many graphing calculators you can see notations like sine negative first or tangent negative first. These are not reciprocals. These are inverse functions. We shall use also a different notation later, arcsine. This is not 1 over sine. Anyway, here comes the definition. Suppose fx is 1-to-1 function. This means every image has only one original, different originals go to different images on some domain df. Then for every y in the form fx in the range of the function, we define f inverse of y equals x. So the function f brings x to y, and the inverse function brings y back to x. In this way, the domain of the inverse function is the range of the original function, and the range of the inverse function will be the domain of the original function. And we have such basic relations. Basic relations. The basic relations actually describe the definition completely. F inverse f of x equals x for every x in the domain of the function f. This is actually the equation f minus y equals x, because fx is y. And another basic relation is f of f inverse y equals y for every y in the range of the function f, which is the domain of the inverse function. So it's good also to write here that the domain of our function is the range of the inverse function. Okay, the range of the inverse function. Another basic relation which is good to add here for completeness is if you take the inverse of the inverse function, you come to the original function f. So these are the basic relations. Now, I can show you how we can work with inverse functions and find ranges for functions using these properties. Here is one example. Given is the function y equals x plus 3 to x minus 5. And the problem is this. Find the domain of this function. So that function is f of x. Find also the range of this function. And find the inverse. So first, I want to find the inverse. Let's look at the domain. The domain is easy to find. Here, the natural domain of this function consists of all x's where we can divide by 2x minus 5. So where this expression is defined. So for the domain, we need 2x minus 5 to be different from 0. So if we solve this for x should be different from 5 halves. So we can describe the domain this way. The domain of this function consists of all x's which are different from 5/2. We're always using braces when we describe sets of numbers. So that's all set of real numbers. And we can write this more completely this way. Let me rewrite it here this way. All x different from 5/2. So from the number line we remove this number. What is the range though? How can we describe the set of all numbers which are values here? And it's not easy to say when you look at the equation of this function. But we remember that the range of the function is the domain of the inverse. So we shall find the inverse. It will have a similar structure, and we shall look at the domain of the inverse. So now find the inverse. How to do this? We solve for x in the equation. In this equation, y equals x plus 3 to x minus 5. To solve for x, we have to do some simple algebra. Multiply both sides by 2x minus 5, and you get y to x minus 5 equals x plus 3. From here, we multiply through 2yx minus 5y equals x plus 3. Then we bring all terms with x on the left side, and this term we move to the right side. 2xy minus x equals 5y plus 3. And then we factor out x. 2y minus 1 equals 5y plus 3. And here we can solve for x. X will be 5y plus 3 over 2y minus 1. This is actually our inverse function. This is f inverse of y. And looking at the denominator, we can tell that the domain of this inverse function consists of all y where 2y minus 1 is not 0, so y is different from 1/2. And this will be the range of our original function. This is the range of function f. So we found the domain of our function, the range of our function, the domain of the inverse, and what is the range of the inverse? The range of the inverse we already know. The range of the inverse function, the domain of our original function. So this will be all x different from 5/2. So we know everything now. We know the main range for the function, we know the inverse, and the main range for the inverse function. This is a type of problem that everybody should be able to handle very well. And then we shall look also at other problems. Before we continue further, I want to show you other functions, examples of other functions which are not one-to-one but can be made one-to-one. Look at this example. Let's say the function f(x) to be sine x, a very familiar trigonometric function. The natural domain of this function is the entire number line. That's how you define it, Calc 1, for instance. And various numbers, it is defined also for numbers. We use all radians. The graph of this function, you know, it's a sine wave like that. It does not undergo the horizontal line test. It's not one-to-one. you can see that f0, sine of 0 is 0, will be the same like f of pi, the same as f2 pi. All these are zeros. So this number 0, which is from the range, has many originals, not 1-to-1. But we can make it 1-to-1 this way. Take the domain to be only between negative pi over 2 and pi over 2. So now take fx sine x with much smaller domain, minus pi over 2, pi over 2. How does the function look? And does it look in this interval? Let's say this is 0, this is negative pi over 2, and here is pi over 2. For 0, the function is 0. For pi over 2, it's 1. It goes like that, level 1. And for negative pi over 2, it's negative 1. So this function obviously undergoes the horizontal line test. If you cut with horizontal lines, you can cut the graph at most once. Also, the derivative of the function is cosine x, which is strictly positive when x is between negative pi over 2 and pi over 2. And because of our derivative test, the function is 1-to-1 in the closed interval. Sine x is 1-to-1 on the closed interval, negative pi over 2, pi over 2. We can define the inverse function. Which some calculators, some notations is written this way. But there is a actually better understandable notation, arc sine y equals x. The range of the sine function, the range of our regular sine function, no matter what is the domain, is the interval negative 1, 1. That's where the function takes values. And the inverse function will be defined over this interval. The domain of arc sine is interval negative 1, 1. Sorry, here, just 1. And the range of the inverse sine is the interval negative pi over 2, pi over 2. So that's important. Now, what will happen next? I'm stopping with this lecture here. Our next lecture will be on the natural logarithmic function. I can tell you immediately that we shall look at this very interesting integral from 1 to x, 1 over t dt. So we have to review integrals with limits, integrals with changing upper limit. So review this. Integrals from a to x, f t dt. How to differentiate such integrals. So we shall talk about natural logarithmic function. We shall call this natural log x. Then we shall talk about its inverse, the natural exponential function. After that, we shall come back to inverse sine, then inverse cosine, and stuff like that. So bye for now.